So friends, now we're going to discuss the practical section where we're going to build two type of classifiers. First one is the happy and sad classifier, which will going to have the happy and sad data sets. And second one will going to be our favorite one, which we are going to discuss. That is your mask and unmask classifier. So this one is known as happy and sad classifier, which will going to give us the result that we're going to feed the happy image, and we're going to say okay, this is happy image, we're going to feed the sad image, we're going to give you the idea about the sad image, right? So this is what the classifier is going to do for us, and there are some packages which you have used. The favorite one, TensorFlow, which will be used to create the model, and I will going to tell you that as the model is going to be there, and I'm going to explain you as the model. I'm going to prepare the models, right? After then there is image data generator. This is basically used for augmentation. As I have told you that augmentation is a technique which is used to increase the data size. When we have a small data size, then we use the very basic principles of computer graphics, which are translation, rotation, scaling, sharing, right? So all these important components of computer graphics are being used to augment the images, that is to increase the number of images. So I'm going to now run this one. Yeah, it's okay. Now what I'm doing, from image data generator, I'm just rescaling each and every image on a scale of 0 to 255, each and every pixel of the image. Basically, when we have an image, it is divided into number of small cells, and each cell is known as pixel, and each pixel has a value of 0 to 255, right? So it is very important that that we normalize the values by dividing them by 255 for image generation, which this particular step is also known as normalization, where 0 stands for black. But if the pixel value is 0, then we can say that that particular, so this is your grid, if it is a 3 by 3 grid, and if this pixel has value 0, that means it is completely a black one, right? So the pixel values range from 0 to 255, whereas 255 is your white and 0 is your black value of pixel, and between them there are number of shades which are going to be used. If we are talking about the gray images, if we are not talking about gray images, then we have three channels on in each and every image, that are R, then there is channel G, and then there is another channel known as B, RGB channel, which and whenever we have filters will going to convolve on each one of them separately, each one on them, and then we get the consolidated result after convolution. But convolution is beyond the scope of this particular lecture, very frankly. For this we need a separate lecture altogether, and since you are here and working on the happy and send classifier from my side, then that means that I'm expecting that you should have a sound knowledge of convonants, and if not, then you can have lectures on that. So now let's move forward. Yeah, what is this? This is setting up the path, and this is where my happy and sad data set is being stored, which I'm going to show you. It is in D drive, and basically it is in here, and there is data here, and this is happy and sad data. This is train set. Again, I have divided. Yeah, these are my happy images. You can see that happy images are there, and then some sad images are there, which I will going to use for my training purpose, right? So this is my data set. Let me run this one also. What is this particular portion? This particular portion is very much important. Here we are doing the augmentation. Here augmentation is being going to be done, right? So how the augmentation is going to be done? This is class mode is binary, but This is basically an image generator, but we are not doing any augmentation here because we are not applying any sharing here. We are just making sure that this class mode is binary, and this flow from directory, we're going to go to the happy and sad data. Inside happy and sad data, it go to another folder known as train. This is a path which I have given to us, and inside this particular folder, it will going to class mode is binary. That means it has two type of data sets are there, happy and sad. For happy, it will allocate ones. For sad, it will allocate zeros, and then it will going to randomize them, create a data for us, so that which we will going to use for training. This is the work of this one. Another thing, another thing which this particular train generator will going to do is as far as preparation of data is being there, because data preparation is everywhere, EDA is everywhere, working on data is everywhere, and whenever we have the structural data, well, like in CSV format, or we have image data. Here, data preparation is being done by this particular statement, right? So, like resizing the images, best sizes, that after how many processings we're going to calculate the loss, right? Or after how many images we're going to have apply the get different type of gradient descent algorithms, or going to tune our filters, right? All these things. So let us run this one. Yeah, it has run. So we have found 219 images belonging to two classes. Okay, no problem. Two classes in here basically means, since we have two folders now, in train folder we have two folders. One is happy, one is sad. So it is saying that we have in total we have 219 images belonging to class. One is having 0 and one is having 1. Let us say, and that one, that is randomized, right? We can't say that it has assigned 0 for happy or 1 for sad. That is instinctively the randomized concept. After that, let us have the idea of test images. Yeah, it has 48 images belonging to two classes. For the, I know that this data is very low, but for the expression point of view, I have kept this data small. Now we'll have to see the shape of the data. Yeah, quick. Now it is something which will going to take a good amount of time from our side, because we are going to explain you the stacking of each and every layer. So our model start from here. We have an input. So let us denote this input by this layer input, and the components we're going to draw by using red line, right? So we have first component, which has, what does means, it has 32 filters. The 32 feature maps would be there, and the size of the each and every filter is 3 by 3. That means 32 feature maps will going to be there, and then we're going to have another component. Now we are having 64 filters on the same size. Then we apply the max pooling. Constantly we are applying here. Max pooling is there also, max pooling is there also, and then we have 128 filters. Okay, so 128 filters means that 128 feature maps would be there, and then max pooling again. After then you flatten all these things, and then we apply them in the 512 neurons dense neural network model, and after then it all goes to single neuron, because we are working only for the binary classifier, where we're going to use the sigmoid function. Why we have used ReLU here? Because we don't want negative values. Pixels don't have negative values. So during training, if filter give any negative value, that is being neutralized by the activation function, which I have taught you in detail, the ReLU function, right? So it is stacking the layers one by one, and this model is known as the sequential model, and each and everything I think should be clear to you. This is a neural network for classification, and this is the stacking of the component. Okay, one more thing. These 32, 64, 128, 128, all are hyperparameters. You can choose any number of filters which you want to apply on any feature maps, right? Normally you have a feature map and which you apply, and then you have max pooling. Okay, after then you take a filter, apply it on each and every image, take its convolve value, right? Take the summarized value, and then repeat this for a number of times, right? What happens that you can have one more thing here is that if this is an image, right, we know that this image has three channels. If it seems to be colored image, we can say that it has RGB, right? Three channels, right? So three channels. But after one convolution, after passing through one connect layer, now it has 32 channels. You can think of this in this way. It has 32 channels, right? Because 32 feature maps are there. And when after max pooling, it's okay, we reduce the size. And then when it passes to 64 filters, that means 64 filters will going to be applied on, and one filter will going to apply on 32 feature maps, going to take the consolidated value, normalize it, pass through activation function, and then it is going to be stored in the grid. And that is to be noted, right? How these filters will going to be applied. Okay, so this is a small idea about the how this neural network works, or this how this component layers, and how we combine the components with the neural network. I know that it is little bit of it is tricky, seems to be there at this particular moment of time, but believe me that if you keep on working on it, you will find it very easy. Now let's move forward. This is callback. I have told you that I'm going to tell you callbacks. So callback are basically used to reduce overfitting, and here I have chosen that if it goes to 0.98, kitten 0.98, it's going to stop. Yeah, so what this I have going to this, please read it carefully. Class my callback tf dot chars dot callbacks. Inside callbacks, I'm making a call to the callback class, and this function which I have used def on epoch and self epoch equals log. This is log which you're going to create, which you're going to store each and every accuracy, since we are working on accuracy. And moment the accuracy get over and 0.98, now loss has been optimized, stop training. And loss have been optimized, that means accuracy is we have achieved the required accuracy, and stop training equals to true, right? So let's run this one also for you. Yeah, now we're going to compile this one, and we're going to, since we are using a why we are using binary cross entropy, I have told you that loss is equal to binary cross entropy we are using because here we are using a single neuron, and single neuron can do only binary classification. So I think that that would be clear to you. Matrix which I have chosen is accuracy. Now this is going to be fitted, and you have seen that it has shown you that 0.994 is the loss in optimized. So I will stop my training. Clear. Now this is the happy and sad classifier for you. Now I'm going to build a new file for you separately, that is for the mask and unmask, and that I'm going to build for you from scratch, and you're going to follow this step by step, right? So firstly I'm going to import packages. So if you want, you can code with me also from you can say in this way also. Import packages, import TensorFlow as TF. Right? Why we need that? Because we need to access different data sets, and then we have TensorFlow.keras or preprocessing images. You can also use keras also from keras dot preprocessing dot image. Import image generate image data generator data generator generator. And then last one which I have used is matplotlib, very important for drawing. Import matplotlib dot pyplot as a plt. Run this one. It takes some time as it is the first time initializing. So meanwhile I'll going to make some fast efforts to resize it, because it's going to take a good amount of time in resizing. Yeah, So image data generator, just going to resize it. Okay, no problem. From TensorFlow.keras.preprocessing import image data generator. This we have already imported also. And train underscore data underscore gen is equals to image data generator, and rescale equals to 1 upon 255. Test underscore data underscore generator is equal to image data generator, rescale is equal to 1. Always remember that these are data generators we have created. Each and every image has to pass through this scaling. Each and every scale will going to normalize. Why? Because if we will not do this during convolutions, when we multiply them by filter values, then values will go sometimes go to thousands. Because suppose when we have 32 feature maps, then we have to combine the 32 feature map values by projecting the filter on each and every feature map, and then you summarize them. So if you not normalize them in the range of 0 to 1, that means in points, then you will going to have very big values in thousands, and eventually the filters, the maximum value is 255, so it will going to overseed that, and it will going to create the problem for you. Then we need to set up the path. So so we have to use for training, set up the for training and test. Not, we are not going to take the tst test. So I have kept that inside this one. So I think that I have to go and see in data sets all where. Yeah, I have to go to C drive, in D drive, in Udemy. Yeah, data, mask and unmask. Right, this much amount of I have to copy, and I just have to paste it here for you. It is like this one. Okay, and you can say that train train underscore data, or train underscore path. Sorry, it's okay. Train underscore path is equals to d underscore, but this will work on Unix based platform, so I have to take it like this. This is our train path. Similarly, we're going to have our test path also, which will be eventually same as this one, only this one is there, test test. Okay, so if we run this, oh I'm sorry, and the path is being set here, dears. So now we have to just run the data generator, which will going to work as a data pre-processing concept, which we have implemented in CSVs to prepare our data, to prepare our images into the normalized data values, pixel into normalized data values. And because whenever we have an image, it pass through, is passed through train underscore data underscore generator. So train underscore data underscore generator will going to first rescale it in or normalize it, and then we will have used the flow from directory, which is a function to take the data values from the directory, and we're going to have a training path. From the training data will going to be there. Each and every one is going to resize 150, best size is 20, and class mode is binary, which will going to assign 0 comma 0 classes and 1 classes. 0 is for say marked and 1 for not marked. So we have found 600 images in these two classes. Now we're going to work on the test also. Okay. Oh, sorry, I'm sorry. We have to go for test path. Control C, because I have removed the validation part here. Control V. I think this will now work. Yes, it has 200 images. Everything looks fine. Now let us look at the outputs. First time, yeah, we have 20 is the base size. Every base size is 20. Size of the images is 50 on 50 on 50, and the channels are 3. That means colored images there, and the output size is 20. 20 images are going to be filled. Okay. Now our model, for simplicity sake, I am using the same model. You can, if you wish, you can change the values of these components. Like you can take 64 here, 128 here, 128 here, 256 here, anything whatever you want. Your model will going to be adjusted accordingly. Now again the callback is there. Control C, Control V, and then let us say that we have decided to keep it as 0.95. Right. It's okay. Let's run this one. This is also ready. Now we want to just fit the model, and now your model is going to be fitted, and I don't think that there is any problem with this one. Only I have to check the paths. Train data generator is okay. Test and for train underscore data generator is there. Validation data test and data is there. Okay, no problem. Callbacks is callback, and this is the callback is nothing but this is callback, and this is the callback which is making a call to my callback, and this is my callback is defined here. It will going to activate this particular portion. We're going to give the accuracy. Okay, no problem, no problem. We are just fitting the model. What is the error it has given to us? Compile. Oh my gosh, sorry, model is not been compiled till now. Let me compile this one. How can I forget to compile a model? Yeah, it is. So since it is also a binary classifier, so no need to change anything. Only the name of the model will get changed. Okay, okay. The model is going to be mask underscore unmask, right? Okay, no problem. And let us now just copy the name from here. Control V. Size is reduced. Let me increase it again for you. Okay. So now this one is compiled. Okay, okay, okay. Okay, no problem. It is okay. Change data generator, test generator, defeat underscore generator, history. Control C, Control V. Okay, so we have model mask underscore mask, and we have now everything is set with us. It is now fitting us. You can see now step by step that how the data is being fitting. It will take some amount of time. You can see that losses are very much high, but as the training will going to be progressed, you will find that the you'll find that the accuracy will keep on increasing and loss will keep on decreasing. Right? So it is model will going to take some amount of time in learning, and you have to very cautious about this. No, what I mean that because see that accuracy is eventually start increasing very rapidly, but you need not to worry that we have already put it the check here, and the check says that 0.95. After 0.95 the model will automatically stop learning. So till it is learning, let us now have a recap of all these things which we have discussed. So this is the package. This is a part where we have imported the packages. This is the part where we have normalized our pixels. This is the part we have set up our directories of the images. This is what we call the train with ready, making the images ready for the convolutional neural networks. And this is the test images. We are making them ready by using the generators train data generator and test data generators. And this particular command is going to take the data from the directories directly. You have to remember this one. Okay, nothing can be done about that. This particular code is basically just checking on the shapes. 150 by 50 by the image of the is the size of the image. Why we are doing this? Because we normally images are of different sizes, so we are rescaling them in particular size, fixed size. Okay, so that our matrix which will get constructed would be, so the matrix which will get constructed would be, we can say that it would be 150 by 150, right? So this is what you have to keep in mind, and this is your label. And convolution neural networks is being used, and the now input sizes, look at this here, input size is 150 150, and channel is 3. That means RGB channel colored image is going to be there. Okay, then we have used max pooling. It is a technique which is used to graph those values which are very much activated. And and this process is being repeated here. You can see conv layer, max pool layer, conv layer, max pool layer, conv layer, max pool layer, conv layer, max pool layer. And then we have the whole big set of features, right? Then what we do here, it can basically, it is being drawn as a three-dimensional image, right? In this way. And then flatten will going to convert all of them into a single vector. Suppose a 2 into 5 into 3 means that two matrices are there. We have the size 5 into 3, that's 15 is there. Then 5 3 15 into 2 30, 30 size of tensor is going to be there. All will going to convert into a single dimension 1D tensor. So flatten will going to convert each and every matrix and normalize them into a 1D tensor, right? This is work of Latin, and then it is feeding into neural network. ReLU is being used. I have told you that we don't want negative pixels, and the last neuron sigmoid will going to do the binary classification for you. So you have to keep this thing in mind, that how we're going to build a neuron, how we'll build the whole network, which is a combination of convolution neural networks as well as a combination of the neural networks. Convolution network convert the image, a single image, into feature maps, and those feature maps are further being processed by different filters of different densities. And the last, we have a full length of lot of feature maps which are going to be flattened and converted into a single dimensional tensor. That tensor contain the pixel values which are normalized in the range of 0 to 1. That is, we have a very big matrix of decimal values which are of course positive, because the ReLU function doesn't allow them to get negative. And then this is fed into the neural network, which can be of any size, 258, 256, 128, 5, 112. Even you go for higher dimension of 1024, and the activation is ReLU, of course, and for each and every neuron. And the last one is of course going to be a single neuron. You can have multiple hidden layers also if you wish. Means that if you want, you can add another layer here, like this. You can just copy it, and you can have another layer like this, right? And some reduced size, let us say in this way, 64, right? And then one, no problem, you can do this one also, but it's okay. Now our model is learning. So now it has been optimized at which epoch, let us see. So we can say that after 10 epochs we have got the required accuracy. So if I have to draw the graph, this is my epochs and this is my accuracy, then I can say that 0.2489 1.0. Then I can say that 95, right, somewhere here, right? Yeah. And at which epoch I have got this one? I have got this one at 10th epoch, right? So at 10th epoch, automatically my model stops learning. And the benefit of this particular thing is that by doing this particular thing, I have made sure that my model does not go overfit, because overfitting is not a good thing. Overfitting may cause loss to generality, and it reduces the efficiency of the model. Overfitting basically means that your model perform very good with the validation data, but when we have moment and we expose our data to test data, then our model considerably got failed, right? So in this particular project, I have tried to implement two classifiers for you. One is happy and sad classifier, and another one is mask and unmask classifier. And I hope you have liked this. And we have given you the theory also, which you should go and try to learn more and more from different books. So let me write the name also. Happy, no, it is not happy sad, it is mask, unmask classifier, right? So it's okay there. Then okay, with this I come to an end of this presentation. Thank you very much.